Hello, everyone. I'm Richard Gillilan from the Cornell High Energy Synchrotron Source here in upstate New York. And I've been asked to give you a sweeping overview, introduction to small angle X-ray scattering, just to get you set for all the other interesting lectures you're about to hear. So to start with, I always show this big picture of what people do with X-rays. It's not everything people do with X-rays, but you probably have seen at the top here, if you shine an X-rays on a crystal, right, which is a packed regular array of molecules, you get diffraction spots, right? And you, in crystallography, you measure the intensity of the diffraction spot, you phase it, you can get very high resolution atomic information. In the middle is fiber diffraction. If you shine X-rays on a fiber where you have partial orientation of the molecules, instead of spots, you will get various bands. And fiber diffraction is a somewhat underutilized technique that's very important today in things like understanding muscle contraction. You can go to the APS and do that on your samples. At the bottom is what we're going to talk about in this workshop. And that is if you shine X-rays on a fluid, a dilute solution containing biological molecules, you know that the molecules are randomly oriented in solution. And the pattern you get in the lower right-hand corner here looks completely devoid of any useful information. From a crystallographer would throw this out, right? But actually, it turns out to be packed full of incredibly useful structural information about how molecules behave in solution. And so I hope when you leave this workshop, you'll be very impressed by all of the useful information you get out of that pattern right there. Okay, so we're dealing with X-rays, which you know are not visible light. Here's a spectrum to sort of give you the big picture. You can impress all your friends by, we often talk about energy of an X-ray in keV instead of the wavelength, but the two are interchangeable. And if you just memorize 12.4, you can convert in your head in between these two. You just 12.4 divided by 1 equals the other, okay? So in X-rays, X-ray solution scattering, we often are working somewhere between 10 keV and 12 keV. And that's about 1.2 angstroms or less for the wavelength of light. Okay, so what I want you to understand is what happens when X-rays interact with matter. There are really three things that can happen, okay? And the most common thing, the most pesky, annoying thing that happens is an X-ray comes in, that's this red wave here. It interacts with, I have a representation of the Bohr atom, right? This is a nucleus and these are electrons. The red X-ray comes in, it interacts with the electron and all of the energy of that photon gets absorbed. And the photoelectron is now packed with 10,000 electron volts of energy. And of course, it goes shooting off into your sample, wreaking havoc, right? This is photoabsorption that results in photoelectron ejection, right? Bad thing. But it is the fact of life that working with X-rays, and you will hear a lot in the lectures to come about how to manage the problem of X-ray damage. And we're getting pretty good at doing that, actually. So, but it's something that you always have to be aware of. The second thing that happens, which I won't talk much at all about, but just so you know it, it's not very important in Sacs at all. It's completely ignored, in fact. And that is Compton scattering, when you have an X-ray coming in, and it can impart a little bit of energy, just a few hundred EV, to the electron, and then the X-ray loses energy and it comes out at a diffracted angle that with a longer wavelength. All right, it's important in high energy work because this starts to dominate when you go to very high energies, but you can really ignore that. It's just sort of a low back level thing in Sacs. Okay, now we get to the important and really wonderful kind of scattering, right? Rayleigh scattering, or sometimes you'll hear it called Thomson scattering. The only difference is whether the electron's bound in an atom or not. And for X-rays, it makes not much difference. X-rays are so energetic. So you have an X-ray coming in and it interacts with an electron, but does not deposit any energy at all. And so but it changes direction. The ray comes out at a different direction. You'll notice the same wavelength, and the phase is shifted, but it's shifted by a constant amount. So the powerful thing, the thing that makes this type of scattering so desirable, is that you have this fixed wavelength and phase relationship. So that, as you will see, allows you to figure out all kinds of structural stuff by looking at interference patterns. All right. So another way that I love to look at this is if you have a wave front coming in, it's an oscillating electromagnetic field, and you can think of the electron as sort of a float, like on a pond, and these ripples come in, and that electron bobs up and down as the X-ray electromagnetic field comes through. And whenever you accelerate a charge, it produces electromagnetic radiation, right? And so it's like ripples. Each electron in your sample is producing these ripples that are coming out, right? Those are the diffracted X-rays. So that's Rayleigh scattering. Right. Now, what about the nucleus? Well, electrons do actually interact with the nucleus. It's just that it's so weak that you can't see it, so it's not useful or even observable scattering. I've often thought it would be a fun experiment to try to observe it. It'd be very tough. But neutrons interact strongly with nuclei. They don't interact with electrons, but they interact with nuclei. And so small angle neutron scattering is a thing. It's a thing that you can do at a reactor there, or a neutron spallation neutron source. So, and everything that you learn in this course will really be applicable to neutron scattering too. Plus, there are some really cool things. If you have enough sample and enough time, there are some very cool things that you can do with neutron scattering, because neutrons are sensitive to the type of nucleus, all right? But I won't talk much more about that, just so you know. All right. So why have I brought us all to this point? Well, this is a diagram. On the x-axis is the incoming X-ray photon, right? And we are here, Sacs is here at about 10 keV or 12 keV-ish. And on the y-axis is an area unit, right? Centimeters squared. And it's called barns, right? It sort of represents how big of a target an electron is to this type of scattering, right? Or how readily something scatters. That's all you need to know. So you'll see that the blue curve is this pesky photoabsorption, right? X-ray damage, the thing absorbs an entire photon. It spews out a high energy photoelectron, which wreaks havoc and does chemistry in your sample. And you can see that it by far at 10 keV is the dominant thing that happens by more than an order of magnitude. And you also notice this is a log-log scale. It falls very, very rapidly with wavelengths. So, which is why when you get a medical or a dental X-ray, you're clear up here. Now, the red curve is the useful scattering, right? It is the Rayleigh or Thomson scattering that is so-called coherent, right? The phase relationship is well-defined. And you'll notice it also goes down, but not as fast. And then down here at the bottom is the so-called Compton scattering, which you see starts to become a dominant force when you're talking very high energies, medical X-ray kind of stuff, right? So there's where medical X-rays are. All right. So the bottom line of this is that you just have to be aware that this damage is taking place and take steps to mitigate it. You'll learn more about that later. All right. So you have a protein here, and you have tons of electrons. And the way to understand scattering in a simple way is thinking of pairs of electrons. And you have a wave coming in. Those pairs create those ripples on a pond I was talking about. And then if you have a detector, you're going to see what's called a speckle pattern if you were able to hold a single molecule up, which you can't really do. You get a speckle pattern like that, okay? And the speckle pattern is caused because for the incoming wave, right? This is Bragg's law. You probably all know this anyway, that this particular wavefront and this particular wavefront are shifted in phase, but not in wavelength, right? This bottom wave is traveling a little bit further. So when they get to the detector, their phases don't line up and you see a dark pattern or a light pattern, right? So now, right. Yeah, so this is just Bragg's law, showing that difference. I won't get into that. Of course, molecules in solution are randomly positioned and in all different orientations. So I've sort of artistically rendered that here as a smeared molecule. So what that means is that your pattern on your detector, you're not going to see those individual speckle patterns, not at a synchrotron. You'll see a smooth pattern that's bright, close to zero angle, and then it kind of fades down to darkness as you go to the edge. All right. So how do we get data out of this, right? So we have our sample, our source, and our sample, and some distance down the flight path. You have the detector. It's really bright, close to zero angle. It fades off. So I've made a little red curve right here, intensity on the x-axis, and something called Q, which we'll just call diffraction angle for now, right? And you can see this forms a curve as you move away. It's less bright, intensity goes down. If you flip this so that the angle is on the x-axis and the intensity is on the y-axis, you get something called the scattering profile, right? That is the fundamental piece of data that you will be measuring in a Sacs experiment. You're getting a single one-dimensional curve called the scattering profile, right? Intensity as a function of this variable Q. It's actually not quite angle. It's a more complicated 4 pi sine of the scattering angle, right? Where the scattering angle here is 2 theta divided by the wavelength. So it's wavelength independent. It's actually called the momentum transfer. I put this page here just for your personal information if you want to know the math and how to sort of interpret it at a finer level. But it's the momentum transfer. But for small angles, you can really think of it as proportional to the scattering angle. You may see H, S, or Q in the literature. Everybody pretty much is using Q, although in some of the programs that you will find out of Dimitri Svergin's group, they use you'll see it referred to as S, but these are all 4 pi sine theta over lambda. Once in a rare while, you will see S referred to as 2 sine theta over lambda. They leave out 2 pi, and people sometimes do that because they like 1 over S to be the resolution, the D-spacing in crystallography. I don't really recommend that. I think, the community is really settled on Q as 4 pi sine theta over lambda. So, all right, that's that. Confused enough yet? I hope not. All right. So Sacs is fundamentally a simple experiment, and which means you can apply it to all kinds of different conditions, and that is the power of the method. You have a source, you have some slits, you have the sample, and then clear down, you let your x-rays go down a beam pipe that's usually a vacuum, and then there's a beam stop made of metal at the end to stop it from hitting the detector, and then you're capturing the very narrow scattering angles, right? So compared to a crystallography experiment, we're really looking at stuff that's very close to the beam stop, right? Usually covered by the beam stop. All right. And we are most concerned in Sacs, as you will see, about getting the lowest angle possible, because the smallest angle possible translates into the largest object possible that you can see. So the larger the object you need to see, the smaller the angle needs to get. And at some point, when you start to get objects that are into the micron range, you need something called USACS, or ultra small angle X-ray scattering, which is a specialized area, very long beamlines. Neutron beamlines can get to those lengths better than Sacs beamlines, I think. And also there is our special optical setups for material science that are not really applicable in biological samples, that can achieve those incredibly small angles that can start to see objects on the micron and larger scale. All right, just so you know. So we typically get to a Q value of like 0.007. Most beamlines do, or they brag a little bit lower than that, which really means objects, well, I would say closer to 300 or 400 angstroms maximum diameter. So, but that's something that you should be aware of. If you have a very large object, larger than a virus core particle or something, then you want to start thinking about, can the beamline reach far enough in the small angle, right? So you will hear emphasized over and over again how important it is when you do a measurement to have a buffer that precisely matches what's actually in your sample, right? Because we have to do a subtraction of the scattering from the sample and the scattering from the buffer in order to get the scattering profile of essentially a molecule in space, right? So, and this is a concept that is a little bit foreign to, most practical molecular biologists. Are, getting a buffer match is not all that important. Well, in Sacs, it's extremely important to get a precise. You cannot simply mix up buffer that you think matches and expect it to work. Fraction of a percent off, and it will mess up your wide angle signal and your buffer subtraction. So you'll probably hear more of that in a sample preparation lecture later in this workshop. All right. So just a little bit about plotting. Most of the time, people like to plot Sacs on a semi-log or a log scale. Biologists tend to like semi-log, where the y-axis is log, because it helps accentuate the features. You can see if you plot on just a linear, it just falls off really sharply and you can't see much. Sometimes, once in a while, people do like to do this. For example, if you have diffraction spots, or some DNA people like it. But by and large, we don't recommend for normal biological stuff. It's much better to do a semi-log or a log-log. Soft matter people like the log-log because that emphasizes the small angle more. So you have all of those options in the software that you'll be learning to use. All right. I'm going to hammer this one more time before you get more lectures on it. If your buffer match is not perfect, if your buffer is not exactly the same as what's in your sample, you will find that your buffer and your sample curve cross or they do not meet. What you really want to see for a dilute solution is that the tails at wide angle, the scattering at wide angle of a sample should be very much like buffer. It should pretty much meet if it's dilute. If you have a very concentrated sample, it might be okay for it not to meet. But in most cases, your curve should look like on the right. That is a good subtraction. So you want to make sure, and getting this match, you need to specifically do it, deliberately make this match. And that is, use the buffer from your last size exclusion chromatography run, which we highly recommend and really require in sample preparation for Sacs. Or you can change the buffer using a centrifugal concentrator to something that you know the composition of. Or you can use dialysis, a lot of people do that, or a desalting spin column. You'll get more about that later. But I just wanted to be the first person to hit on that very important topic. Right. Now, I'm going to talk about the nature of the scattering curve. Right. So the scattering curve I, that's intensity as a function of Q, scattering angle or momentum transfer, is a product of three things. There's a prefactor, a form factor I have in red, and a structure factor I have in blue. Right. The prefactor is related to, it's a constant. It does not depend on scattering. It tells you about the molecular mass of your sample, the concentration, the sample contrast, which you'll learn about later, and things in the experimental setup, like how many photons are coming through the apertures and things like that. So that's the prefactor. You'll hear a lecture later on how to get things like molecular mass from that. The form factor is what everybody is after, and that is the form factor gives you the shape of the object, its maximum diameter, its radius of gyration, the degree of folding, which is a very powerful thing. And you can even do atomistic modeling and get averaged electron density these days. Just amazing that you can do that. So this is what you will hear the most about in this lecture. It's what everyone is after. The structure factor is usually ignored in introductory courses. For dilute solutions, it's approximately a constant, 1. But you do have to prove that your solution is dilute enough that you do not need to worry about the structure factor. I'll talk a little bit about that in a minute. The structure factor actually gives you information about when it's when it's not one. It gives you osmotic compressibility, radial distribution of molecules, interaction, interesting things, but we're not going to talk about that in this workshop, right? So the intensity of okay, let's talk about the prefactor, right? So I've given the full formula in all its glory here, but what all you need to get from this is that capital M is the molecular mass and C is the concentration, right? So it's a product. So your prefactor, your Sacs profile is scaled by the product of the molecular mass in kilodaltons and the concentration in mgs per mil, or if you want, daltons in grams per mil, all right? And then there is the only other thing that you need to be concerned about is there's this delta rho, which is a contrast, okay? And I'll talk about that in a little bit. But so simplifying things so it's easier to see, M times C, right? Your Sacs scattering profile is multiplied by this mass times concentration, right? And so what that means is that there's for an optimum concentration, a good signal in a Sacs pattern, that your concentration is inversely proportional to your molecular weight. So, for example, if lysozyme, which is a small molecule, 14.3 kilodaltons, if a 4 mg per mil sample gives you a good scattering curve with, a nice looking Guinier plot, as you'll see, not too much noise, but it's also not too concentrated, then, this 1/m relationship means that if you're measuring glucose isomerase, which is 173 kilodaltons, quite a bit heavier, it's a tetramer, that you really only need 0.3 mgs per mil to get a decent signal. So just keep that in mind. The higher the molecular weight, the lower the concentration you need. And you want to always measure multiple concentrations, at least 3, sort of bracketing what you think is the best concentration. You want to aim for something that is not too concentrated and not too dilute, right? If it's too concentrated, you will see the structure factor starts to become non-constant. We have something called concentration effects, which I'll talk about in a minute. And if it's too dilute, it's really noisy and you don't have good accuracy, or a good signal to noise level. Okay, so that's so some people have sort of a rule of thumb, like good concentration is like 30 divided by M or 60 divided by M, right? Everyone has a good, but mine is basically 4 mgs per mil of lysozyme, 0.3 of glucose isomerase, and you go from there. All right. Now, contrast. Remember I said there was a term called contrast, right? This is the difference in average electron density of your buffer minus your sample plus buffer. All right. No, I'm sorry. Buffer minus your neat sample, right? So the technical term for that is scattering length density, but really you can think of it as average electron density times a constant. So if you calculate the electrons per unit volume in different things, like water is 33.4, and protein, you see, is 420. It's close but higher, right? So the difference between water and protein, the delta is the contrast. You'll notice that nucleic acids are even higher. They're very electron rich. That's great. You get a stronger signal. But notice that lipids are smaller than water. So you actually, they're a bit smaller than water. You get a strong signal there too. Now, suppose I have a solution of 65% sucrose at 420 electrons per cubic nanometer. Look at that. It's the same as protein. So what's going to happen if you look at protein in a sucrose solution like that? You're not going to see anything. So sort of the bottom line is that contrast is not a good thing. You want as much contrast as possible. And so you want to keep your salt and buffer less than 1M, work with minimal concentrations if you can. Glycerol can be a good thing to protect against radiation damage, but keep it low and be careful when you have mixtures of things, DNA and RNA and detergents. Those are special cases I'm sure someone will tell you all about later. Okay, that's the story with contrast, right? This term right here. All right. Now, form factor, I'm not going to take a whole lot of time because you'll be getting lots and lots of lectures about all the wonderful things you can get out of the form factor. All right. So that's what you're going to be after in this workshop. So form factor is basically Fourier transform of the electron density. Well, someone said it's technically a Hankel transform or something. It's a one-dimensional transform with a sign in it. And you can write down the analytic formulas for these integrals, right? A sphere with a constant density. The soft matter people spend a lot of time developing. They have whole dictionaries of models of tori and concentric spheres and ellipsoids and rods and all kinds of even disordered things in which they're fitting to their models, right? So generally, we have much more well-refined models in protein crystallography. But just so you know, all right, simple formula, all right. And you see these oscillations are, virus particles, big things like that, you might see these oscillations, and that's why, all right. And I won't spend a lot of time talking about shape reconstruction. You'll get a special lecture just on that. It's kind of amazing that you can do it if you put the right constraints on, so I won't waste time on that. Now, the first thing that you will do when you are measuring a dilute Sacs pattern is you will utilize the approximate law of Guinier, right? Andre Guinier, who was really sort of the father of modern small angle X-ray scattering. You can look up his thesis. It's published, and I looked it up in the library, and here it is. So he noticed that the scattering looks sort of like a bell curve. So and the width of the curve is related to something called the radius of gyration, right? And the radius of gyration, as you'll see in a minute, is sort of a mean squared difference between all the electrons in the center of mass. So it's a measure of the size of the object. And so therefore, if you plot a scattering profile, if you plot the logarithm as a function of q squared, you get a line. And the slope of that line is related to the radius of gyration. And that is a very, very important and useful thing to do as a diagnostic. I'll show you in a minute. So the radius of gyration, just so you know what that is, right, is, like I said, you take the center of mass and you subtract the distance of all the electrons, sum the squared, and that's Rg squared. All right. You can think of that in terms of electron density. You can think of it in terms of pairs of atoms. You can think of it in the pair distance distribution function, which you will learn to calculate later, right? But the thing to remember about radius of gyration is that it is small, smaller than you might think. It's smaller than the hard sphere radius of your molecule. So don't be concerned if a radius of gyration looks smaller than you think. It's supposed to be, right? Now, these radii apply only to lysozyme. They can the orders can change, okay? And comparing, for example, the hydrodynamic radius to the radius of gyration can tell you important things about the overall shape of the object, right? So that's useful information you can get from other techniques like dynamic light scattering and NMR. All right. So getting analysis, there are several pieces of software that you will use to do this. I'm showing you the BioSAXS raw software, and you'll get a little menu that pops up where you have this logarithm of intensity as a function of q squared, and it's linear. You see the difference, and it should be sort of a nice line, right? And you get the radius of gyration from that and the intensity at 0 angle. Two very important properties that you will need. Okay, so why do we do this, right? Well, it turns out that it's an incredibly important diagnostic for how good your Sacs data are. If you see this lovely straight line, it is a good sign that you have a clean monodispersed sample. That is only one kind of thing in only one conformation and one oligomeric state. That's the ideal. It's not a guarantee of that, but it's a very important check. If you have a smile like you see here, it is a bad sign. It is a bad sign. You need to diagnose what's wrong. You need to run a chromatography because this is a sign that you have something that's non-monodispersed. It's a mixture. And usually a mixture, the very first thing you should try to do is go back to the lab and purify and see if you can separate the mixture. And then if you can't do that, then there are ways of dealing with mixtures, which you will learn later. On the right, I have an example of something that you might see quite often, which is if you forgot to centrifuge your sample, you have some dust or bubbles or really large aggregates or precipitate, right? You have, it looks like a straight line, and then you have this little upturn, right? So you might actually be able to fix that. I'll show you an example, right? Here is a Guinier plot of a sample someone took in my Beamline a long time ago, and you can see the linear fit is not good, right? It's a smile. This means it's not monodispersed. You can see radius of gyration is 93. That's rather large, right? You're starting to see 50, 60, 70. That's a big thing. You should start to kind of think, is it really that big? And so I suggested as a last resort, this person go to an ultracentrifuge and spin this thing at 100,000 RPMs for half an hour. And look what happened. Isn't that nice? You see the difference, right? Suddenly, the Guinier fit got really nice and linear. And look, the differences are uniformly distributed on, on both sides of the line. And look what's happened to the radius of gyration. Now it's down to 68. It really fell a lot from 90 something. So this is an example of aggregation. I show here the scattering profiles on the semi-log plot. You can see the turquoise one is once it's been centrifuged and monodispersed. You want to see that turnover, whereas the magenta one just sort of goes straight up. If you see a scattering profile go straight up, that is never a good sign. All right. You want to see this sort of turnover kind of parabola starting to form at low angle. That's what you want to see. All right. Okay. Now, I just want to show you how to present data. Oftentimes data is not perfect. And you can see here, this is an actual published thing where there was that linear region. It was a very sticky, difficult to purify sample. There's some signs of aggregation there, but it wasn't important to our conclusion. So we just presented it. We presented it this way. Now, I could have cut off the data like that, right? And that's really not an ethical thing to do, right? You should not, if you've got an upturn like this, you should present it to your reviewers and to your readers, and let them know, hey, this data set had some kind of aggregates, and it might be okay. Depends on, the reviewers may say, okay, we still believe you. This all of your data makes sense, but that's what's important. This is ethically versus unethically. Please refrain from the desire to cut this thing off. That's even though it might look nice. All right. Okay. So radiation damage is sort of the primary thing that can cause not good looking Guiniers. And I give you, this is a somewhat noisy example. As you expose a sample, you'll start to see the intensity at low angle rise, right? And what's happening is those photoelectrons I warned you about that are really energetic shooting around in the sample are chemically activating proteins and causing them to stick together, changing charges, making bonds that shouldn't be there, and so forth. All right. So so that's just something to be aware that can happen. All right. Now, what concentration do I need? So I showed you sort of how to estimate concentration. This slide really shouldn't be first. I'm gonna jump back to this in a minute. All right. So remember the formula that I showed you before of the scattering curve is the prefactor, the form factor, structure factor. Now I'm going to talk a little bit about the effective structure factor, just so you know, right? This is a case when you have a concentrated solution, when your proteins are starting to get close enough together in solution that you are beginning to see scattering from electrons that are on different molecules, right? So this term is not becoming one. So here is an actual example. The green curve is the dilute, right? What we call the form factor, right? It's nice and dilute. The magenta curve here is the concentrated solution. What you notice, this is a very characteristic sample that oscillates. It comes up and forms something called the interference peak, and then it dips down. And just so you know, the dip down is related to what's called the osmotic compressibility. You can think of proteins as being like an ideal gas, right? And if you have an ideal gas and you try to pressurize it, right, they'll resist getting close because they have light charge. And so, but there are areas of high density and low density, right, that is related to the sort of compressibility of that ideal gas. And so this dip, when you get a concentrated solution, is telling you about that compressibility, right? And then this first peak is telling you about the separation between proteins in the sample. And you can estimate 2 pi divided by this peak position in Q will give you the approximate separation between your proteins in solution. So just when you start to see concentration, you might see this. That's what you're looking at. But generally, we're going to try to avoid that by taking a series of dilutions to assure that we know what the dilute curve looks like. And so here in green is the dilute curve, and you'll notice it's noisy, right? That's a problem with dilute curves. And then we've taken a concentrated curve, 47 mg per mil of lysozyme. That's pretty concentrated. And you notice how it dips down like this. But the wide angle parts agree. So the advantage of a concentrated curve is that the wide angle data is really good. It's really low noise, but the small angle data is distorted. So it is perfectly okay in a long-standing practice to merge these curves. If you really want to do a great job of creating a good overall Sacs pattern, you may merge them. Very few people take the time to do that, but just so you know, you can do that. And in fact, there are some tools that allow people to merge curves that you can find on among the ATSAS tools. Okay. All right. Oh, yeah. Just so you know, this is an example of there's a debate in the literature about whether or not lysozyme actually has clusters, transient clusters in it. An interesting and lively debate that's been happening for a number of years. And here again, we have a concentrated solution. Actually, it's polystyrene spheres, but you can see the green is the infinite dilute result, and the red is the concentrate, right? And there's the interference peak I told you about, and it dips down because of that osmotic compressibility. And the squares are a known documented case of when clusters are starting to form, transient clusters, just so you know. So that's how I sort of, this is the general take-home message that you should have from concentration effects, that when you have a good random distribution of things that are not too close together, right, you get the middle curve. And if you have charge repulsion, and the particles are too close together, you get this dip in your curve. And then when you have attraction, as in the formation of clusters and aggregates, things go up, right? So it's really the only thing that you need to know for this course is that this can happen, right? And you need to take concentration series to make sure that you understand what's happening. You might have concentration-dependent oligomers. You may have not enough salt in your buffer, and so the proteins are repelling each other, and they're forming ordered arrays that are causing small angle scattering effects. So that's why we generally add a little bit of salt to the buffer. Okay. All right. So I just want to end this lecture telling you that one of the great strengths, maybe the greatest advantage of Sacs, is that it can probe all kinds of conditions, unlike crystallography or cryo-EM, where you have to screen for conditions and then freeze things. Sacs is sort of like NMR and other solution techniques, allows you to try all kinds of different conditions, and that is its superpower. So, my facility specializes in high pressure and high temperature and anaerobic conditions, but there are all kinds of things you can imagine testing. So I just want to leave you with that idea. Thank you very much. If you ever happen to be in upstate New York, come collect some data at the Cornell High Energy Synchrotron source. Thank you.